People think when they think of AI, it's probably happened in the last 10 years or 20 years, but it's a journey of almost 70 plus years, right? Then came 2012 AlexNet paper. This was the first time a GPU was used. So for all the guys who was invested in NVIDIA stock, this is your origin story. You have so much of information that there is no experts anymore. This layer of as micro SaaS play, it will not be there anymore. But this SaaS is definitely dead.
So let's start with an oral history of AI. Who coined this term? How did this whole term of artificial intelligence come about? What's been the evolution?
Yeah, yeah. I mean, people think when they think of AI, it's probably happened in the last 10 years or 20 years, but it's a journey of almost 70 plus years, right? The first initial evolution of intelligences as early as or even before evolution of computers. That's the 1930s, 1940s time when Alan Turing was working around building machines to break Enigma. If you have seen the imitation game, that's exactly is the origin of AI at that point of time. So the thesis behind that approach is okay, fine. You have a bunch of cryptic messages flowing between systems, which is Enigma, and then you had
And
multiple
this
versions
is
of Enigma as well.
the Nazis had this very
Yeah,
famous encryption device called the Enigma machine, through which they would plan World War II, where they are attacking, where they are deploying their submarines, etc. And for the Allies, it was important to crack the code of the Enigma machines, and Alan Turing was the one who cracked the code. So that just a little bit of background for the listeners. Yeah. So please continue.
absolutely. So that
Mm.
was the background, right? So fine. So they wanted to scale the encryption or decryption of these messages at scale because there were so many messages happening and there were so much amount of configurations around Enigma. Manually, they could able to scale up. So that's when Turing came up with concepts of can machines think, can machines solve. That is the fundamental theory of AI at that point of time, right? I think Post followed up with that with the mission is called Bomb, BOMB or something of that sort. I forgot the exact spelling of the name that Turing has created. I mean, if you watch the movie, it's the rotators that move and try to decrypt a message or a setting. That's exactly is the first computer that people have ever created. Post that, it became post World War era. So this got into the
But
mathematics. Yeah,
just Turing also created the Turing test, right? Which for
correct.
a lot of time used to be the gold standard for AI. Of course, now very easily, even a free LLM or a basic LLM can pass the Turing test. But the Turing
Yeah,
test was essentially that if you are talking to a to somebody whom you don't know, and you cannot distinguish whether you're talking to a machine or a human being, that is the Turing test.
correct. Again, so all of this came during that period, right? So World War has been done. Now people needed to expand this theory. People have heard about this theory that the small community in Bletchley Park, which is the MI6 or slash cryptographers university at that point of time, which is responsible for decrypting messages across World War. That news got spread out and said, okay, fine, let's expand and double click on that theory. People started gathering as a small community to try to discuss and evolve this further. So this was then the AI as a term has kind of coined 1950s to say, fine, so can we give intelligence to the machines? If so, what is the approach? How do we test it? That's when Turing came up with the Turing test as one of the methods to test the intelligence. So that actually marks the beginning of AI. In fact, I would actually mark this era itself as the theory of AI because a lot of fundamentals on how or what we are doing today, it's the theory of those were already discussed and math of it is largely discussed at that point of time. In the last 70 years, it's primarily our learning is in terms of how well to implement a concept called deep learning. So that's what the evolution is. But the initiation happened around 1970s. In fact, when it started, the approach was the same. So fundamentally, what people would think is, okay, how does a brain work? Can I replicate a similar learning behavior into machines? That was the initial approach. That was the background for artificial neural networks, right? So that was a time, 1949, 50, I think, where neural networks as a concept was introduced, saying that, okay, here is how a neural network should be. And around 1950s, people started defining a mathematical function to this called perceptron. So perceptron is, one of the when you combine these neural networks into layers, that becomes a neural network. So people started building a small scale neural network machines using a ZOR kind of circuit maps, where you have on and off kind of learning machines to do a simple task. So this was how they started doing it.
One,
This was
one
way
question here.
early. Yeah.
What is neural network? Like, can you go a little, zoom in little on that?
Oh, sure. So if you look at any biological brain, right? So a brain is made of a bunch of neurons. Neurons is like a learning function inside a biological brain. The learning is interaction between these neurons, right? Which is where you have the electric circuit triggering between the neurons. That becomes the learning in our brain. That stores in our brain in some places. And incidentally, what happens is in the brain, there are a lot of localizations, right? Like a certain part of the brain is responsible for a vision related task. Certain part of the brain is responsible for hearing related reasoning and all that stuff. So this is how a biological brain is made of, right? So that's the early inspiration when people thought, let's build AI, because they thought, let's replicate biological bodies and build that into machines. This is the time when there was no scaled computer, right? So 1950s is where you didn't even had a computer. So they were fundamentally thinking of a math or a biologically inspired math and try to create a computer out of it. So thereby they were introducing a lot of concepts to understand how neural network works. Like the perceptron is one bit of evolution there, and then you have something more important called backpropagation. Backpropagation is the learning optimization, meaning in your neural network, when you pass the information forward, your backpropagation actually adjusts and corrects the learning inside the network. So the theory of backpropagation was introduced at that time. But again, most of these are theories in a very early stages. People have discussed them. There was a bunch of frontier, a theory without limitations. When they started implementing it, that's when the limitations came into play. Primary limitations is the compute itself. So as I said, it's not even an era of a consumer computing. Forget about high scale computing at that point of time. People try to implement these theories and logics in small scale, small capable machines. The theory promises a lot of vision, right? Saying that if we do this, then we can achieve this, achieve that. Uh, this is again spiraled a lot because of early successes of Bambi, the Turing machine. People thought, okay, they can achieve similar kind of successes in multiple problem statements, but it was not able to scale as well as what people have thought at that time. So there were a bunch of early stage experiments as well. So there was a small robot built. There was a small, fully autonomous robot as well. But again, these are like a very lab kind of tools. Uh, and most of this research is primarily funded by public organizations. Like early DARPA was actually focusing around evolution of AI, for example. UK
And
government was investing a lot
DARPA is
around
the
AI.
U.S. government defense
Correct.
advanced research project, something like that is the full form. It's a U.S. military subsidiary or a part of the U.S. military.
Correct. So this is largely funded by public. So if you look at the trend line, right? So you had an early success during the era of during the wars. Now they want to commercialize or create and scale up those concepts. There was a reasonable funding for the next 20 odd years from 1940s to 1960s, 70s as well. There is a bunch of reasonable funding backing the idea of neural networks primarily, largely neural networks as the idea to build AI. But then in 1970s is the first AI winter. There was this report called Lighthill Report, which is published by UK at that time, which evaluated and looked at all these projects, and they said this is not at all scalable. The promise of building AI is absolutely not reachable. It's all of this is pretty much theory. It was very harsh report on a bunch of AI projects at that point of time. So this is the beginning of the first AI winter, right? So the theory promise was so much so that there is a bunch of funding, and then it kind of checked by the reality when they started implementing it. And as it is largely backed by public funding, so they are answerable to eventually the public and the government. So they just simply stopped funding many of these ideas. So this just kind of stopped a lot of experimentation that was happening at that time, right? So this winter was almost for next almost a decade. Almost a decade, there was but again, so I think the fascination to build intelligence is pretty much, so much so. People have seen 2001 Space Odyssey during the same time, the 1960s, 1970s. Uh, you had, you had so much of fascination around sci-fi. But nevertheless, I think we have seen the second set of AI wave alongside with alongside with commercial slash evolution of personal computing, right? 1980s, 75, 80s, when Apple, IBMs were focusing on personal computing, where people started looking at, fine, so instead of building AI specific computing, let's focus on maybe personal slash consumer focused compute. So 1980 is when again there is a large amount of focus around compute. People started building computers. Now experiments like this didn't require a large amount of funding, right? This marked a bit of democratization in terms of AI research. It was earlier largely focused by certain universities, backed by a lot of backing from the governments. But with all the compute being available to some extent a little bit cheaper as well, as compared to eras of 1960 and 70s, there are a lot of democratization around experimentation. So people started trying out multiple experiments, multiple theories and approaches. So this is a second way of AI again. So the early success was the expert systems. This is the early AI commercialization as well. So far, we have not seen so much of implementation of AI in a large scale commercial aspects. But during 1980s, there is expert systems. Expert systems is instead of building learning systems, you give a bunch of rules and build expert systems for a specific process. I think there is a system called XCon, which was built during that time. It was largely trying to package a bunch of orders during the e-commerce orders game. So again, because of the boom of computers, people were ordering a lot of stuff. So ability to package and create a right combination of these is also a problem to achieve that scale. So people build this expert systems and solve that problem at scale. They were able to scale up a lot of um, you can call it as a minimal automation. They were able to automate a bunch of things. But this export systems as a theory and an approach, people even use today, right? So even today, for example, if you look at in places like financial services, for example, you have a rule-based fraud systems or rule-based underwriting systems, which are necessarily export systems. They identify a bunch of rules or guidelines that is required to accept a transaction. and they validate the transaction on these guidelines or rules, for example. If as long as the transaction satisfies it, it goes through as a strike through, right? So that's where you have a bunch of rules being used as an underwriting system today. So yeah, I think the evolution of expert system as a concept is quite used even today's era as well.
What is
But
the
at
what is the difference between an expert system and an algorithm?
uh, In export system, you define the contours manually, right? For each and every step, or you can think of it like a, let's say, a decision tree kind of process, right? You we are kind of double clicking, but let me say that in an approach point of view. So let's say you have a decisioning system, an export system, to underwrite a transaction. So you follow a set of methods saying if this then that, if this then that. You have a bunch of IFTT rules, right? These rules people typically define it manually. For example, let's say your FICO score is less than 700. So typically, if it is greater than 700, I'll go to a next set of rule. Now it is less than 700. So manually, I'll have to identify if it is less than 700, what is the next set of risk criteria I have to check before I go to the next step. So these contours or nodes, an expert or a human will identify manually and define these rules. Sometimes these can be a little bit abstract. That's what happened in the recent times, let's say last couple of decades in financial services. So instead of simply defining that as a if-then rule, it could be an observation from analytics, for example. But still, even then, it is manually defined, right? This is a rule-based expert system. Algorithm is I don't need to define this manually. So can I have a system to do this automatically in a manner that I can achieve the same set of output, right? Uh, the same expert system replica is something like gradient boost tree based models. Like you have XGBoost model, which is the most used classic ML technique across different use cases. In XGBoost, instead of defining this decision tree manually, so the algorithm tries to identify where should I segment the data and create that next set of tree functions so that I can achieve a better prediction with a lesser amount of error rate. So Algo does a similar thing in more fully automated way, whereas in expert systems you are trying to define everything manually. So this is the big difference. Now this is what the problem is as well, right? So at that time in 1980s, the Algo is not that much matured. People thought expert system is the way to achieve this. They said, okay, fine. So why don't I define this expert system for every given process in the entire world? But you can't define that manually. It's very hard to scale it up. Again, this was the early 90s where now there is a revised amount of investment and interest post the AI winter in mid 1970s and early 1970s. Uh, People started investing again in AI. But now it's not just driven by neural networks, right? So there are now two classes of experimentation. And in fact, a major amount of experimentation was actually around the second class, which is the expert based systems, not on the neural networks. So neural networks kind of became a very much a taboo at that point of time. So people thought, these theories doesn't scale up from a neural network standpoint because there are a lot of intrinsic limitations to implement neural networks. So they started investing around, yeah,
What is the IT manifestation of a neural network? So you told me neural network, like the brain has neurons which talk to each
yeah.
other, and then there is localization. Like, say, your speech is in one area of the brain. All the neurons in that area specialize in speech. How is this manifested in the software world? Is it like a bunch of chips representing neurons, or like what?
Yeah,
Like,
no, it's much fundamental actually. So as I said, so in 1960s or 50s is when the definition of perceptron came into picture, right? Perceptron is one neuron. One neuron is perceptron, and you combine multiple perceptrons, it becomes a neural network. Okay.
and what does
So
the
perceptron,
perceptron do?
yeah,
Like,
perceptrons is a very much a simple linear function. You can make it as simple as f of x is equal to sigma of f of y plus bias b. So weight weight is the weight, and then you have the bias. So let's say you have one, two, three, four neurons and one, two neurons next, right? So how much weight you allocate to this neuron and how much bias you can allocate. That weight and bias allocation is happened over time when a certain data flows from one neuron to another neuron like that. It's a simple math trying to optimize an end function where you have a weights at each node and bias at each node.
So
So
a
yeah,
perceptron is just like a mathematical function. There's some data
a
in and
simple
some data
mathematical
out.
function.
Data in,
Yes,
data out. And perceptrons, a bunch of perceptrons together is a neural network.
correct.
It's not just a bunch of perceptrons together, but also those perceptrons are given weights. Like some perceptrons are more important for some work.
Yeah,
Like say,
and that allocation of weight is what the algorithm needs to do, right?
okay,
What weight need to give to which neuron at what point of time.
okay,
So this is exactly is what happening in the last 70 years, right? We know that and in a retrospective, we always knew that deep learning is meaning neural network based systems is the approach, but we never knew how to implement it properly. So in the last 70 years, that was has happened. Like early there was a theory, and then we had introduced perceptron in 1950s, and then backpropagation is so how does the data flows forward and error flows backwards, so that these weights will get corrected, and thereby the model starts learning. The learning is nothing but you act and react, right? And you do it a little differently next time.
so
That's
back
what the learning
propagation
is.
is feedback, basically. Like,
Correct. Exactly. Backpropagation is
okay.
feedback.
Okay.
Correct.
That this was
So
a wrong
this
answer. So let me go back and see which perceptron was responsible for it. So to
Yes, and
fix
adjust
the
the
weight.
weights and everything.
Okay.
Yes.
Okay. Hmm.
So, this has happened in 1950s, right? So this is like almost 60, 70 years old theory. That's what I was saying. I think in early AI era, it was largely a theory around neural networks. And then we hit a wall because of a lot of things, which is primarily around compute was one big problem, and second was the data. These were the two main problems. This was the 1970s, right? So then people thought, why invest only on this approach? There is another approach which is expert-based systems that had an early success in 1980s. Why not invest in that and see how well it can get scaled, right? So the theory or investment around neural networks was very much reduced in 1980s because of what happened in the before 30 years. It became very much a taboo, and very few people continued the research around the neural networks, which were called the bonkers of the academia at that point of time. uh, but during that time, a lot of fundamental concepts were again rechecked and introduced. Things like, for example, you had Jan LeCun working in 1980s, who is doing work around CNNs. So he introduced he's even though backpropagation was introduced early on, it was not fully implemented in a neural network approach until 1980s. So in early 1980s, there was a Japanese researcher, Fukushima, I think, if I'm not wrong. He has implemented backpropagation neural network in early 1980s, which was extended in late 1980s by Jan LeCun by stacking these layers called CNNs, convolution neural networks. It's a new class of neural networks to do image classification task. This is on digits recognition. Like in the early 90s, if you look at the check processing being done in US, was large to some extent was automated because of this idea. So
This
this
OCR, optical
correct.
character recognition technology, this OCR technology was based on this CNN technology.
Yeah, so CNN to some extent, and there was also classic, as I said, the expert systems, right?
Expert
So
systems. Okay.
people expanded that expert systems to classic ML in late 1990s.
What
Between,
can you zoom
yeah,
in a little bit on CNN? What is this convoluted neural network? You said is the full form.
yes, convolutional neural networks.
Convolutional. Okay. Hmm.
Yes. So, so in neural networks, that's the idea, right? So if I combine these neurons in a different kind of manner, I will have a different kind of learning behavior, right? For example, if I stack them one after the other continuously, that's a recurrent neural network. This is again introduced during the same time itself, during 1980s or okay, I'll stack one next to another, and I'll propagate the learning from one block to another block, another block, another block, and then I'll try to learn. This is one type of network. And then in convolutional neural network, you typically this is used for images where you have a matrix of three-dimensional matrix, which is RGB, right? That's what an image is defined to. You have a bunch of and pixels is pretty much an each node in this point. So you have, let's say, so this much amount of depth you have 1D or 2D, typically 2D kind of convolutional neural network. You have one layer starting at your entire image kind of dimensions. Then you will have another block of neural network, which is lesser number of dimensions, such that the learning will start isolating to learning certain kind of behaviors. So you stack them up like that in a certain order, and you try to create an learning function or optimization function between these layers, so that the learning happens from one to another. I'm talking about a very advanced concept, but at that point of time, all of this was maybe less than 10 by 10, 4 by 4 kind of neurons at that time. So to scale it up is where people had a bunch of challenges. Meaning, in early stages, if I scale to these many neurons, if I don't know how to do, let's say, a gradient optimization, then eventually it will not learn anything. I'll simply have a bunch of neurons which doesn't learn anything, and it will give me a back wrong result. So this is where the propagation was one idea, and then there is things like gradient boosting was another one. Gradient implementation was another one, which was introduced by Hilton in later on in 2000s, which is around DBMs. But again, so coming back to taking a step back, if you look at 1980s to 1990s, one class of thought is around expert systems, where there was an early success and then there was a bust. Expert systems were also not scalable. Neural networks was not scalable. So, but neural networks didn't have any kind of pressure. People who didn't had who had very strong beliefs, only they started investing around neural networks. The next phase is what the important one, which is the 1990s till 2010s, for example. For almost next 20 years, there was a slow innovation happened one after the other, one after the other, one after the other, which is primarily around classic ML, which is primarily around things like you started having algorithms like SVMs, support vector machines. You have random forest models, classic ML techniques evolving. This is because of both evolution of data and computers, right? So computers became mainstream. There are a bunch of computers. There is a huge amount of data. .com kind of picked up a lot. All of this gave a little bit more resources than what they were before 1990s, for example. And these classic ML systems started seeing a bunch of successes, right? So success after the other, success after the other in a very small scale. People primarily in the financial services areas, for example, people started building things like the expert systems in fraud, the expert systems in underwriting. In financial services, this was scaled very well. And then statistical modeling, people started implementing that in algo trading since 2000s. And even today, algo trading is now a big area, right? On the consumer side of things, you had things like search engines, which again uses these basic fundamental classic machine learning concepts. Um, but it was not actually what happened from 1990s also is that AI was not looked at one department kind of approach. So people started diversifying the approaches largely specific to data sets as well. Like for image data, there is OCR, which picked up a lot from 2000s as well. Even today, OCR is the biggest thing. from a computer vision standpoint, enterprise implementation of computer vision, for example. And then you had search engine, which actually reinforced a lot of investment around NLP. Because how do you type in the keyword, how well you can retrieve the information, which is what the main focus was for people like Google in 2000s, for example, how fast they can do, how accurately they can retrieve the information. So that gave an introduction to a bunch of NLP related problems. Because now it's not just tabular data, right? So until largely till 1990s, 2000 also, it's largely tabular data heavy kind of work. Because early adoption of computers was around tabular data sets, right? Like your classic accounting, for example, stock markets. It's a tabular data heavy industry in 1990s to 2000s. Computer vision was to some extent because that was the early digitalization era. People started scanning things, storing images as files. So it was an early computer vision related task. 2000s is what the NLP era was, the beginning of NLP era, because of the search engine evolution, for example. So net, until the recent wave of 2010s, till that point, which is 1990s to 2020, 2010, it was an early era of slow innovation. A lot of things started happening very slowly, very systematically, without a large amount of hype around AI. Right, there was no hype wave for the almost 20 years between 1990s to 2010s, which actually was helpful because there was no overflow of funding, there was no overflow of experiments. The experiments were driven by organic research, one after the other. Particularly for deep learning, this is actually very important fundamentally because even though the concepts were introduced in 1950s, 60s, people started implementing those concepts. Like, as I said, backpropagation in 1980, for example, the early introduction of CNNs. And then the CNNs were scaled into a little bit large scale again by Jan LeCun's team in 1998 as part of the Bell Labs research lab. They again scaled the computer vision problem around image classification at that time, and that's kind of slowly, also because the image data is kind of populating. Now, if you see the evolution of data population, unstructured data like images is getting bigger. The quantum of data. Text is getting bigger. Tabular data largely there, but there is a bit of monetization happening on tabular data because of the expert systems or classic ML. Whereas the CV, the computer vision part, and NLP is very underserved, right? We had more data than the monetization capability around it. There was search engine for NLP. Images, there was largely nothing except OCR. This is what kind of triggered many people to say that, okay, fine, there you have more amount of image data, more amount of text data. So how should we start looking at this? And this looked like a very good scale problems, right? Because you had good enough data, good amount of diversity, and there is reasonable amount of commercial interest around these areas. So this is when 2000, early 2005 or the ImageNet data as a project started in 2006, if I'm not wrong. It later completed in 2009. Uh, so Feifei is one of the well-known researchers in AI from Stanford, if I'm not wrong, when this project was started. So the idea is, fine, if we want to solve the computer vision problem, you need a good data where you can build models, experiment, and
You
create
need
a
data with labels.
benchmarking.
Hmm.
Yes. Create a benchmarking, right? You need a very strong benchmarking metrics to be able to scale the algorithms. So for images, there was not, the data set was pretty much non-existent. So this lab, Feifei took that initiative. They started labeling thousand classes as in thousand different concepts. Like in those thousand different concepts, you had elephants, flowers, objects, a lot of things. So the idea is they had somebody manually or to some extent augmented, very rude augmentation. They look at an image and they classify and they label it as, okay, this is elephant. They did that for almost a million plus data. 1,000 classes, a million plus data. I mean, look at the efforts, right? So if this data was not existent, I don't think we would have had this much amount of research around neural networks at that point of time. Uh, so ImageNet data got introduced. People started experimenting the algorithms around ImageNet data. Now this is like a classic movie story, right? So we had initial hero introduction, which was in 1950s, where neural networks was the way to solve it. Then the classic problem in a movie, which is your theory is great, but implementation is poor. It's because the world never caught up with it. You had certain things which the world didn't had, but a lot of self skilling was happening, right? Like how to implement neural networks, how to do it effectively, how to do backpropagation, what are the different network architectures that you can come up with, like RNN, CNNs, RL. All of them were introduced in 1990s, early 1990s, for example. Now, the theory was there to some extent. The implementation is getting there. Now we need a problem statement to say now we can prove and say whether we are successful or not, right? ImageNet was that data set where people started benchmarking different approaches. Then came 2012 AlexNet paper. This is the big,
But
yeah,
one question: how is ImageNet a problem statement? Like people would run their algorithm on the images to see if their labels match the human labels. Was that the problem
correct.
statement?
So
Okay.
yes, so ImageNet competition is it's a classic competition, right? So annually they will look at all submissions and rank which submission has scored highest in this performance. So you had human labels. Now you benchmark that with your machine predicted labels and see whether machine predicted accurately as compared to human labels or not.
Okay.
Till 2009's, 10s, 11s as well, the accuracy or the error rate were around 25%, 30%. So this is again, they were doing things like manually defining certain things. This is again to some extent like an expert kind of system
That if it
where
has
it,
two eyes and four legs, then
yeah,
it's
exactly,
an
something like
animal.
that.
Okay.
So, so things we used to use techniques like edge detection first. So you use some techniques to do edge detection, and then post edge detection, you will try to identify multiple things like what is the color, maximum of color. You write different different things for different aspects of it, right? This is what I said. If this then that, but approach was statistically driven. Edge detection done by some statistical model, and then you go to the next step, and then you go to the next step. You summarize it, and then say, okay, this probably could be an elephant. This probably could be something else. So till 2011, the error rate is around 30%, 25, 30%. So which means it's okay. It's not great, but it's not at all reliable, right? Accuracy is only 70, 75%, 25, 30% error rate is not a great one. Then came the AlexNet paper. The error rate suddenly drops to 15% at that point of time. 15, 14 odd percent, 86, 88%, if I'm not wrong, the accuracy was. But the interesting thing is the approach. This was the first time a GPU was used. So for all the guys who was invested in NVIDIA stock, this is your origin story, right? So for the first time, a GPU was used to implement a neural network, applying all the concepts that were introduced till that point and implemented on a large scale data and a reasonably good enough compute. This GPU was a 580X, if I'm not wrong, RTX 580. This had hardly around 3,000 or 5,000 compute nodes. Maybe less than that, if I'm not wrong. So maybe 580 or something like that. Less than 1,000, if I'll have to cross check that number, but very less number of GPU nodes, right? Even NVIDIA was not looking at this as a use case area at that point of time. The thesis is, okay, neural networks needs a lot of parallelization. So if we can parallelize this on a reasonably large enough compute, we can have a little bit larger model and make the model learn faster. This was the problem in CPUs. If I increase the number of layers and if I add more number of nodes, it will take inevitably very, 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 very long time. It was not scalable. So people thought, okay, that's why neural networks will never be scalable, because you can't do this on a CPU of 16 cores CPU. At that time, it probably a 8-core CPU with a clock speed of less than 1500 clock speed, which is very, very small clock speed and a small CPU. So you can't have a model built on this. So 2012 is when people like Alex, Ilya, and Professor Hilton. Hilton was one of those guys who had been investing around neural networks parallelly as much as Jan LeCun, for example. For a very, very long time, there are very few set of professors who were in deep learning and continue to invest in deep learning. Hilton Hilton introduced a bunch of new ideas as well in 2006. There was a paper around DBMs, deep belief networks. It was a different kind of way of training a neural network model. So NetNet, AlexNet introduced in 2012, where accuracy suddenly jumped. That triggered a lot of attention in the academia.
One question I have: AlexNet ditched the expert approach.
Yes, it's not an expert approach, right? I'm simply build a very large neural network. In fact, this is the interesting idea as well. So they built close to 7 CNN plus one fully connected network, close to 6, 7, 8 odd layer neural network. They have not defined what to do at each layer manually. There is no manual definition of anything of sorts, right? So I simply pass my image and I correct the error in my final layer looking at the label, predicted label and actual label, and propagate the error back to my neural network. When they train this model at a scale of the ImageNet dataset, and this model was able to scale with a large enough data, right? So then when they started looking at what's happening at these layers by looking at the attention maps, they learned that each layer is doing a certain job automatically by even though we are not defining it manually. For example, certain layer is responsible for learning more around the edges. Certain layer is responsible for learning the human objects. Certain layer is responsible for understanding, the colors, textures, for example. So whatever we used to do manually through expert-based systems, now if you scale the model large enough, it was able to do that automatically. This was the trigger for everyone, right? So people said, fine, now you can build a very large neural network and you don't need to define this manually. And you can apply it to a reasonable data as long as the data size is there. So this is the most probably the beginning era of new age AI, new age startups as well. So 2010 12 is when, yeah,
So there was in the 90s and 2000s there was this Deep Blue, IBM Deep Blue, which
yeah,
beat Gary Kasparov, the world chess champion at that time.
yes.
Was that an expert system or was it a neural network?
No, that's an expert system as well. It's in chess, right? The number of strategies are pretty much limited, or at least the number of strategies required to beat a human is very limited. So it's more of a search function. So you had multiple strategies and you try to apply that search function depending upon the strategy that is currently implied upon. So this is again 1997, 98. Deep Blue was there. And post that, and there was an intermediary bunch of news as well, right? You had Watson winning the Jeopardy game in 2010s. I believe if it's around 29, 2010s as well, around the same time. That's an NLP problem, right? This is what I'm saying. 2000s to 2010s, a lot of attention was around NLP because of the search. Huge amount of data is now indexed, which is the web. People are trying to use that web. There was Wikipedia came out for Jeopardy. Wikipedia dataset is a major required dataset, right? The approach that IBM took at that time is something called knowledge graphs. Even then, people use today the knowledge graph approach to for certain kind of models, for certain kind of systems as well. The knowledge graph approach is, you try to identify a bunch of entities, which is, the things like city names, country names, actors, like that. Jeopardy is primarily around questions around knowledge, right? Like general knowledge between objects like movie stars, locations, poets, like that. It was primarily around nouns, in short, right? They created this knowledge graph systems using that as the approach, and they were able to win the Jeopardy game. Same thing, to win a human expert in a game, for example, the number of searches or the search function is little. It depends on the problem statement, of course. First was chess, then was Jeopardy. Uh, Probably the most next complex one is AlphaGo, right? In 2016-17. That's again is a search-based system, but it has a different kind of approach. We'll discuss that. But these two were the main things that happened in that 1990s to 2010s kind of era.
A knowledge graph is just a system of organizing knowledge, information, like if
Yeah, to
information
some extent, yes. It's
organizing
an
classification.
indexing. You try to keep the concepts closer, which are related. Then you try to create that as a mesh of network, such that when you need something, you hopefully see that whichever is closer is the closest to answer that problem. For example, uh, so knowledge graph. Uh, yeah, so they in early NLP era. So this knowledge graph used to happen using a lot of things. Like this is again the time when we started as well. There is something called ontologies. Ontology is nothing but dictionary. Okay. So, for example, I have an English dictionary, which is keywords of all the English language, right? Then, if I want to explain certain industry, let's say computer science, for example, in computer science, you have things like artificial neural network as one word, which is a concept, right? You have a bunch of concepts. So people started creating in 2010s or 2000s these ontologies. So they had things like medical specific ontology, general knowledge ontology, movie story ontology, for example. So ontologies are the base for creating these knowledge graphs kind of systems. So this is again an early era where NLP was largely a classic NLP was largely through this kind of approach. You use things like entity recognition, grammar recognition, and you use those inputs into the algorithm. Grammar recognition, for example, what is a word? If it is a verb, you will keep that word. If it is prepositions, for example, you will remove it because that largely has any impact on the search function. In when you're searching or asking something, right? Your noun is main important. Like for example, what is the capital of France? France is a noun. Now, next is what is it that you want to know about that noun? Next is the capital, right? Capital is the next one. And next is what is it for the capital that you want to know about that noun, which is what? You want to know what for the noun France. The information that you want is capital. So this is the classic NLP approach. You can convert any a text query input into a format like this, and that's how people were doing search. It's not rudimentary, but at that time it's very advanced. Um and to do this relationship, right? So, what is the relationship between a capital and a France in a given query? People used to do very manual NLP techniques and libraries. I remember that there is a library called Spacey. Even people use that Spacey today. Spacey came in around 2010s and 15s. But at that time, there were a bunch of libraries that we were even using as well, because whenever there is a text information, you have to understand that in some manner. This is what we were using it. The reason why I'm explaining this is now closely related to what we are doing in LLMs, how we are doing in LLMs, right? So you understand, I think you always have an initiation of an idea. There is a spread out of the idea or a maturity of the idea, and then the scale of the idea. So this is what happened in AI from time and time and time.
What is the difference between a CPU and a GPU?
Oh yeah. Okay. So CPU is largely a series-based system, right? So you have, let's say, 16 core CPU. Your laptop is powered by motherboard. Motherboard requires a CPU to do things like your programming and all that stuff. Most of the series functions, like all your classic requirements, are a simple series-related kind of functions. When you need a lot of parallelization as in I want to do a bunch of functions at the same time and aggregate it and do next set of functions, aggregate and do next set of functions. Like streaming a video, for example, or simulating a game, for example, simulating weather, doing a bunch of calculations across multiple data sets. This is a parallelization problem. To do parallelization, I can do that in CPU, but I have to have limited number of cores, like maybe 32 cores, 16 cores, depending upon your RAM size and your CPU processor. Whereas for a GPU, you will have more number of cores, right? Like 1080 had close to 1,000 odd cores. And today's traditional consumer grade GPU, like 4080 or 4060, for example, has somewhere between 2,000 cores to even 4,000, 6,000 cores as well. So if you increase the number of cores, so this is again the story of NVIDIA as well, right? So one is, okay, let me increase the number of compute cores. Again, this is the same time when NVIDIA has started, right? From 1990s. 1990s, the idea is why only have a CPU-based processor? Why can't we have a parallelization kind of processor? Their first GPU processor is late 1990. Until then, for almost 6, 7 years, they were simply doing R&D and product building. They were the initial use cases for GPU was gaming, because in game you have to load a bunch of frames, and frames has a bunch of pixels. So instead of loading those pixels one after the other, so they try to load those pixels multiple times parallelly, such that you will have a very seamless experience when you are playing a game. So this is the approach for GPU. So where you do a bunch of parallelization, and NVIDIA was investing a lot on this because of the boom in gaming. AI was never in the picture until 2012 as well. There was early analytics being done on GPUs, but not to the scale. So GPU was NVIDIA was primarily trying to support the requirements of a gamer, always that as a preference and a priority until 2020 as well. The gamer was a priority. They were launching a bunch of consumer grade GPUs and large enterprise grade GPUs as well, primarily for large scale processing kind of tasks.
Okay. You mentioned on AlexNet that they saw the attention map. What does that term mean, attention map? Like you said, there were 7 or 8 CNNs, and then they looked at the attention map. And again, this word attention is also kind of important in AI. So that's why I want to
Yeah.
understand it a
Sure.
bit.
So, yeah. So for each, when I pass a new input to the neural network, right? So I've trained the model. For example, while training, I want to understand what each node is getting activated. Activation maps, in fact, not adding. My mistake. So activation maps. What it does is, whenever an information is flowing through that neuron, it sees which neuron is activated to what information input. Okay. So, for example, let's say I have a pixel and I'm passing that pixel through the neuron. So, which neuron is activating for that pixel for what kind of information? So, when you map these activations, you would know that which neuron is activated for which kind of input, right? So, let's say for edges, it is activating a lot, which means this neuron is responsible for detecting the edges. Uh, okay, this is what the explainability comes to, right? Uh, uh, okay, this is a new concept in AI, which is explainability. Okay, model is giving me the classification, but on what basis the model is giving me the classification? In expert systems, it's easy to interpret because I know which rule or which function is activated, and basis on that, I know on that basis what is the output. Like, for example, your credit scoring. Even today, credit scoring is very much an expert-based system. If your credit scoring is getting 10 points better, you know that this is because I have given 10% score to your renewal rate. Whenever renewal rate, meaning your collect how well you are paying your credit card bills. If that is on time, your score is always good. If that is not on time, then your score will get affected by 10 basis points. And the rule triggered is this: you have a very clear traceability going back to the exact area or input where the model has taken that call. In neural networks, there are multiple ways you can understand that. One is using this activation maps. Activation maps is when you run the input, you observe which neuron is getting activated, and you highlight those neurons as responsible neurons, right? Uh, Same thing. Likewise, in neural networks, you have another method called integrated gradients. It calculates the gradient values and tries to cross pollinate that again. You have a bunch of different ways to do this. By going through the neural network and trying to understand how the neural network has, given you that output. Summarizing what happened in, let's say, 2000 to 2010s, plus or minus 4 or 5 years, was a focus around NLP, because focus around search became a large amount of attention, because you suddenly saw a lot of data being indexed, right? And there is Watson, which demonstrated the value of knowledge graph systems in Jeopardy game, and they did a bunch of marketing around Watson. Watson, even today, people use Watson for different things, but a lot of backend technology has changed in the last few years, anyways. So 2012 marked the beginning of the AlexNet paper, right? Now you will see a very much a template. Okay, so there is this lab who created an algorithm which beat the industry criteria, and that approach is well appreciated and used for many other use cases as well. And followed with it, another lab introduced a new technique, and have beaten the AlexNet outcome in 2013. This was the team from Clarify, if I'm not wrong. So Clarify is a startup. They exist even today. So 2012, 2013 is when many of these, whatever you have seen in the last 2 years was happened at that time for us when we started. Because in the academic community, deep learning was suddenly became a big focus, saying that now we can learn, we can build large scale neural networks and learn things like images, which was not scalable till that point of time. So many people came with different approaches of commercializing it or investing around R&D. This is when people started investing around R&D back again in a scale as much as in 1980s. This was the only time, or largely, I know many people were investing at the same time, large enough amounts, with a very focused and very important research and commercial applicability. So when you had this algorithm, right? So CNNs, for example, scaling for problem statements like images, there are two things that is quite important for us to scale to next stage, which is the commercial applicability of it, right? So commercial validation is always important to cross invest in the R&D and upscale the R&D, for example. Uh, while the CNNs were implemented for image-related problems, the parallelization and implementing deep learning large scale on GPUs started scaling up. And people started applying that for different kind of problems, not just for images, but also for things like text. I discussed the NLP approach, right, where you use things like entity recognition and then do lexicology or ontology based kind of NLP. People said, why don't we do a similar NLP task using deep learning, using neural network based systems? This was the work when a few people started working around it, like people like Richard Schosser. He's now the founder of U.com. At that time, his work was one of the good work around NLP. Like, as I said, so when somebody asks something, you need to find the relationship between the different components, right? Your noun versus verb, what is the relationship is what you need to identify, and you were using classic NLP techniques. So instead of doing that, all of that using manually, now if I train a model, in this case, it's RNNs. So CNNs is largely parallel kind of learning problem. RNNs is primarily for series related problems. Like language is always a series related problem, right? For
What is the full
example,
form of RNN here? Like,
recurrent neural networks.
okay, recurrent
Yeah.
means what here? Like,
Recurrent meaning you have a blocks which is connected to one to another, and the learning function is one after the other, and the backpropagation happens, and then it's more like a block of neural network. Okay.
okay, okay,
Uh, so, like, language is a series problem, right? For example, I am the, president of United States, for example. I is related to am is related to the related to president related to United States. Everything is recurrent, right? So the idea of that is if I remember this sequence of data right, I then know which word is responsible for which kind of activity, right? We are now talking about a little bit high dimensional space. So initially, I used to do this manually by saying "am" is, let's say, this, and United States is the noun, for example. I used to have a dictionary and pre-labeled data, and I use that to create a logic, which is algo or something like that. Instead of doing that, now I'm building an algorithm, right? Uh, so early NLP work was this. So I'll train a very large neural network and in a very high dimensional space. So I'll put each text into a vector, vector of let's say 100 dimensions, 1,000 dimensions, like that. Then I use that vector as my input into the neural network, which we call as an embeddings. I convert the text into embeddings, and I feed the embeddings into the model, which is the neural network, and I'll train the model on those embeddings. When then once the model training is done, if I look into this embeddings, right, something like, let's say, once model training is completed, then when I give a word, there is a embedding vector that it will be generated. When I plot that vector into this high dimensional vector, we started observing that the model is contextually was able to understand a lot of information automatically. So, for example, when people trained this recurrent net model on a very large data, like Wikipedia data, for example, Wikipedia data itself is a very big corpus, right? So after training and when they start plotting this graphs, so let's say all the nouns, for example, they observe that the embeddings vector of all the nouns are in the same location, which means the model was able to understand that this is a noun, and certain other things also. So this is a very interesting idea right now, which is what happened with images, where I don't need to define the borders, texture, color separately. I can do that by having a neural network that can learn it. Now I can apply the same thing to language as well. So this was the beginning of a new kind of era of research around NLP now. So there is one stream of research which is around CV, one stream of research around NLP, and then the other stream which was continuously around speech, translation, and all that stuff. In translation, also we have seen a very good amount of success by using things like RNNs, for example, things like neural network based systems, for example, again for speech. So this is the like 2010s is when people started 2010s, which is after AlexNet 2012, 2015 is when many people started understanding that there is a value of commercializing this, and we believe there is a lot of value in commercializing. Which is where startup like ours, for example, we started, and then there was people like Clarify, MetaMind. There are a bunch of like 50 odd startups who were early deep learning startups. Very much like what you have seen in the recent times, right? Like a lot of foundation companies came up because there was one research output. Same thing. So there was a research output. There are a bunch of labs who were already doing a similar kind of research, and they said, okay, now let's commercialize this because we have reasonably good amount of model in place. So initial approach was model as a moat, meaning I have a better model as compared to others. So you could use me to have a better performance in that output. So we were focusing on a different kind of problem. So we were looking at building an AI assistant for STEM researchers. So we were coming from an academic background. We were doing research. So
What is your
typically,
what do you mean by we here? Who all are there? And like, when did
yeah.
you discover the world of AI?
Oh, yeah. So this is way back in 2012, 2013. So I was then in IIT Bombay in third year and moving to fourth year. So my program is a dual degree, which is BTech plus MTech masters. So as part of the masters, you have to do research, right? So which is before your pre-final year, before your final year, you will do a thing called literature review. So the typical process is you'll go to a professor and tell them that, look, I'm interested in this topic. I would love to do research in this topic. So what should I do? So the professor will tell you to read a bunch of papers for the next 6, 9 months and ask you to figure out an area where you can work with him on that research. Okay. So this is a way that you would typically do a research in a PhD or a master's or a research project, for example. I was stumbled upon AlexNet paper when I was going through that literature review. So the idea was my specialization has to be in computer science, meaning I have to pick up some topic which is related to computer science. And I was fascinated with AI to some extent because it was very early idea. There's a lot of fascination. And I thought maybe this is something that I could think of to do some research around. And I was stumbled upon AlexNet paper at that time. But I have to apply that for my research problem, which is in mechanical engineering. So I started using the CNN architecture for my research thesis. But that's when I was introduced to deep learning. This is again very small community, but what happened is there are back to back a bunch of increase in number of papers talking about this concept and this idea, for example. So that was the same time when we were facing the problem. At least I was facing the problem around literature review, right? Uh, so I read bunch of papers around around NLP as well in terms of how we can learn the language and everything. So the idea at that time was if I want to do literature review and come up with a topic and go to a professor and spend my next 1 year, 2 year on that topic, I should do that literature review as good as best as possible, which can stay true for the next 1 to 2 years, right? Uh, but the problem is, we have seen so much of papers being published. I think at that time, close to 30 papers were published on a peer review basis, which means 30 new papers where new ideas were publishing across topics. That itself is a so much amount of new knowledge, right, that is coming into the market. Forget about what's happening current. So I'm talking about scenario 12 years back. Then the idea was, we were using tools like Google Scholar and Scopus, Google search engine. So search engines at that time are also simply keyword search engines. Like in 2012, when you type in things like capital of US, you were given ideas which were having the keywords like capital and US, and the ranking is a page ranking algorithm, right? More investment for Google was on page ranking, not on the NLP part, because NLP part was not evolved at that time. We said this is not ideal for a research area, because let's say if I'm typing something around how to do speech recognition using AI, I didn't mean any of it in research, right? What I mean by that is I'm looking for an algorithm which can help me to do, let's say, a token to token conversion from audio to text. That's my intention. But I can't type all of that in search engine. I may not even know this information from an academic point of view. So that was the idea. So meaning, one, you have so much of information that there is no experts anymore. And the search engines were very much a rudimentary kind of tools today. So why can't we use this technique, deep learning, and what is being used in NLP, and scale it up to things like search engine, and eventually to an assistant kind of sorts? Okay. So our journey was in 2013 is when we started the company. 2014 is when we raised the money. Early 2014, and we were seven researchers at that point of time. Uh, when
One
we were hiring this, yeah,
one question: how did you raise money? Because
yeah,
um, it sounds very academic to say that uh, researchers need a way to access research and be up to date, etc., etc. I mean, it doesn't seem like commercial opportunity or the
yeah.
TAM which a VC uses, that doesn't seem to be there. So I'm just curious about that.
Sure. So when we started, I mean, the idea was to start something which can solve the problem for researchers and build an AI assistant and a search engine, right? Uh, we went to few researchers, few VC, few angel investors at the point of time. So this is way back in 2013, right? So the VC community in India was pretty much non-existent. Angel community was pretty much very, very small. There was only Indian Angel Network at that point of time as a network, and there was Mumbai Angels who was doing few investments. There was Thai Global, the Indus Entrepreneurship kind of thing. So this is pretty much purely accidental. So we were talking to few angels at that point of time. We were explaining that we want to build an AI search engine for researchers and eventually an assistant. But our initial approach is to build a community around a platform, collect data, and build a community around it. So that was the idea, and we at that time we called it as inventzone.com. uh, it's called as InventZone. I think if we still own that domain or not, I'm not sure. That was the idea. So when we went to them, we told them here is a problem statement. Problem statement is there is so much of information that is there in the industry, in the market. The current tools are very, very redundant. If I use these tools, I may spend next 6 months to find an answer or to find the right information, or I may not, I may never able to find the information as well. This problem is only going to grow further and further, right? We want to solve this problem. To start with, these STEM researchers, they only like that we are technical, coming from a university with a background in research, and from IIT Bombay. That's it. So that was only plus points. Otherwise, there is no validation at all, right? So there was no tech company at that point of time in India. There was no AI company at that point of time. So there was no funding around tech-driven companies. It was not there for even for the next following few years as well. They liked our honesty, and the investment was also quite small. It's not that much. So we raised it from around 20 odd angel investors. And that was good enough for us to get started with. But that's when the actual problem is, right? So the problem was fine to some extent to raise the money, but the problem was to solve the problem, to build a company that what we want to do. Uh, Now let's look at the scenario, right? There is no university which is teaching about deep learning. There was no compute accessible in cloud. Today you can get a GPU on cloud. Imagine 12 years back, where you don't even have a GPU was not available 7 years back as well. So that only happened in the last 7 years. So GPUs were not available anywhere. We have no clue in terms of how to start coding and how to start implementing those. We were simply hiring people based on largely math background and computer science background. Uh, we were always that odd one out kind of team. We were hiring people who may not be very well in academics, but very good at coding, for example, who may have built very good algorithm, but their academic score is quite poor. We were the odd team, seven people. All of them were recently grads, pretty much. All of them are recently grads, in fact, correct. We were our initial way of approaching the problem is by reading papers, by going through open source that attached to those papers, by playing around with a bunch of tools and implementing it. So there was no TensorFlow, there was no PyTorch, there was no a scalable deep learning framework at that point of time, right?
What are
Uh,
these terms? What is TensorFlow?
so TensorFlow, PyTorch, or the libraries that you would use to build a deep learning model, like Spark or Scala, for example.
These are code
Uh,
libraries.
Yes, Python libraries.
Okay.
So when you want to write a neural network, for example, instead of writing in C++, you can write it in Python using these libraries.
Okay.
At that time, we were using C++, or there was an NVIDIA framework called Digits at that point of time. So we were using Digits
And
because we needed
one
CUDA
more.
programming.
Okay,
Yeah,
one more question. This deep learning here, as a term, refers to the neural network frameworks, all of these, like the RNN, CNN, all the innovations which happened collectively. You're talking about that as deep learning.
correct. So neural networks is, you have a bunch of perceptrons talking to one another or learning from one another. Deep learning as an academic concept consolidates everything which uses a neural network based approach like RNN, CNNs, all of them are under deep learning as a concept. Okay.
Okay.
Yeah, so we started with so what we have done is we went into we kind of set up our own work machine at that point of time. We bought 1080 at that point of time using for deep learning. Probably we were the only guys at that time in India who's using deep learning on 1080s. It was being used in US for sure, some bit of areas in Europe. Research was happening there. We brought in 1080 GPUs in the market, and then we started using those in building these models. So our approach was we started to build the AI assistant for STEM researchers. So we scraped the entire internet and indexed close to 34, 35 million research papers. At that time, total number of research papers was around 45 to 50 million. So there were 50 million research papers. We were able to scrape around 30, 35. It looks like a good enough. So this scraped information is sometimes, with without consent and all that stuff. This is like classic. You will go through a website and scrape whatever is available to scrape, and then you use that information for indexing. So we picked up this 30 million research papers and we built an RNN model, which is probably one of the biggest at that point of time for researchers. At that time, there is Wikipedia-based vectors. This is called word-to-vec model. People have used word-to-vec model to convert a bunch of data sets and build the embedding space that I said, right? The weights, the pre-trained model that in the current scenario, like an LLM. At that time, it's the word-to-vec kind of model. So we scraped the internet, we indexed a bunch of research papers, and we built this model. Now we started using that model as the base for our search engine. Okay, so like the RAG, which is there in the current scenario, we were using that in the similar kind of concept. So the idea
What
is you
is
use
RAG?
retrieval augmented generation. Okay, so RAG is okay. So in the current scheme of LLM, when you ask a question to an LLM, so you would have indexed a bunch of snippets from your data basis on the vectors, and you do a cosine similarity between your input and a bunch of indexed vectors, which is nothing but a closest contextually similar information sets from your data. You will pick up top three of them and ask the LLM, give this information to the LLM as part of the context, saying this is the question, this is the similar information that I retrieved from my data. And LLM will use the question and the similar context to answer the question. This is the rank. So one way to get an answer for an LLM is directly taking the answer from the model, from the pre-trained weights or fine-tuned weights. But the problem is it may not have all the knowledge required for your question. Let's say, for example, your domain specifications or your notebooks or anything like that. So instead of training the model on this data again or specifically, you would use a technique called RAG, where you shortlist information and you give the information to the machine to summarize and give you the answer.
Okay, I
In
remember
our case, yeah,
early days of Chat GPT. There was this thing that prompt engineering is the next big profession, and
yeah,
you will need to learn prompt engineering, which today nobody talks about, is because of RAG. I guess RAG is
no, because of
doing.
reasoning, in fact.
Okay.
So I'll come to that as well.
Okay.
But RAG is something that people use even today. Like if you want to use any kind of LLM in an enterprise application, like a question and answer system, chatbot, or anything like that, you always use RAG or you do SFT, which is supervised fine tuning. uh, or an SLM, if you have good enough data, for example. SLM is a small language model.
Okay.
But this is the current method. At that time, we were doing a similar kind of methodology. So we had a bunch of research paper abstracts. We are doing search engine, right? Which means as long as I can extract contextually similar data, I can answer your question, which is the search query. We were probably one of the first search engines who was using the contextual based similarity search engines. Specifically for STEM research, we were the only guys at that point of time. So we started doing few things interestingly after that as well. So the idea was we combined classic NLP plus deep learning model to create something called knowledge graph itself, but in a different kind of manner. We said for a STEM researcher, when they ask a question, it's not the paper that has most amount of references is important, but the paper that could get most number of references in future is important, right? For example, if I'm typing something, if it has let's say 10,000 references, which means it would have been a old paper, that approach and theory would have already been used by many people. I would rather be interested in a paper which is recently published, but has something which is a base for me that I can build and build something unique. Like novelty is everything in STEM research, right? You have to add the delta, or else nobody care about your research or nobody care about your paper. So how do we build that kind of capability into the search engine, right? So by mapping the knowledge graph, we were able to map and predict what is the next topic of focus. For example, when a user types ANN, artificial neural network, we know that if I take the projection for next 5 years, next relevant topic could be deep learning, because I see more papers being published in deep learning. Within deep learning, let's say an RNN, for example, right? Which means if I see that you are looking for a deep learning, I'll probably go to RNN and the domain focus that you're looking at. So we call this as a predictive search. So in the search engine, we gave you an option that predict the search queries for next 5 years, 10 years, like that. So your search ranking will change, which was a very, very interesting idea. So saying that, okay, fine. So if I want to do a relevant search today, this is what your top paper would look like. And now, if I change my requirement to, let's say, next 5 years, where would I see more papers getting published and all? I would see new kind of topics emerging in my search criteria, right? Uh, so, but there is always a questions of relevance of the trend line and everything, because in research, most of the times the disruption is always a new trend line, right? A new trend line would always take over than the trend line that is following. But if you're in that trend line, it's better to look at what's happening in the next 5 years, any which ways. This is something that we created, and then we want to take it to an conversational kind of system. We said, the search engine is still a very rudimentary way of interacting with the data. Why can't we have a question and answer kind of system, right? Uh, that's what we have done as part of the next step of iteration for the product. We build a STEM assistant where you ask things like, which algorithm is more relevant for my research area, like this, right? In the backend, I was doing something like an expert system, right? No, I used deep learning to extract certain things. I augmented a bunch of things using classic NLP, and then I was giving them the answer. The problem is it's not dynamic. The NLG part, natural language generation, is not existent at that point of time. I can't generate the text rightly. If I could do that, then I could combine this and then simply give the answer in the current state of scenarios. This was not there because of the limitation of what's there in the deep learning at that point of time. So this was the case until 2017, right? Until the attention is all you need paper got published. So during that period, we
And
gave up on that idea. Yeah.
what is that? Why is that paper important?
I'll come back to it.
Mm.
But from 2012, 2016, 17 onwards, many people were in a similar stage, right? Like ourselves, for example. They had a very strong academic background, would have published certain algorithms, certain ideas. Now they are trying to figure out a commercial applicability of those ideas in different departments. Some of them were solutions, like Clarify came up with an image labeling solution for e-commerce. They have seen that as a good use case, and they scale the use case. Even today, they are still existent and they were able to scale it up. And there were people like MetaMind, for example, which is Richard Schosser, who was doing a lot of work around NLP at that point of time. He was building a deep learning platform, so that's called MetaMind. We were using that for STEM research, like a search engine slash assistant as an end use case. Uh, even though there is a lot of revolutionary tech or approach came out, the success of it was very limited to one or two use cases. Image labeling was one, and to some extent, search engine was next. For the next few years, search engine has transformed from keyword to contextual, all of that stuff. So search engine got some idea, and text classification has got better. So wherever people focused on these commercial problems, they were able to scale and build an enterprise product out of it, and able to scale things out of it, right? And then there was another class of products, which is the tool-based startups. Like at that time, for example, there was Histo.ai, there was Databricks, Data Robot, there was Data IQ, for example. They were looking at classic ML and big data as a product. So now we are looking at three layers, right? So you have a tooling, algo, and applications. So these are the three different things that started happening at that point of time.
What is
Everything
the
is
service provided by the tooling layer? These are like
oh yeah.
ontologies.
No, no, no. So this is like libraries, for example, or platforms where you can build models, or even largely platforms primarily. For example, you would use a data robot to connect your data sets and build models. They were using classic ML and slowly migrated to deep learning till late 17 and 80s. We pivoted in 2015-16 from the idea of building an assistant to tool, because when we reach to this stage, building an assistant, building a search engine, we realize that this problem of building an assistant is not solved today yet, because there are three things that we are primarily trying to solve but couldn't solve. One is the memory problem, right? Meaning when you're asking a conversation, your follow-up question is always follow up to a previous question, which would have been a follow-up to previous one. So you are asking questions to sequence basis, right? Uh, in conversation, this is important. You need to remember what is spoken in the past and continue that conversation. This was one. Second is the NLG part. We are not able to generate the text accurately, because we are not able to understand. Like so far, whatever we have done is we understood the language, but we weren't able to replicate the language. We were able to create a new language. The same thing is also happening in images as well during the same time, which is we understood the image and classified it. But if you asked me to create an image at that time in 2014-15, I couldn't do it. We couldn't able to. So the generation part, NLG or image generation, is not existent at that point of time. So things that became successful was, which were doing classification, which were doing contextual search, for example. They were successful both in images and tabular data sets. And then there is a tool part like Data Robot, for example. We became one of those tools very early on, because we know the challenges of building a deep learning model, like not having a TensorFlow or Torch being there. So we build an framework called Braid. It's very much comparable to Keras. So Keras is another meta framework. It sits on digits and simplifies the way of building a deep learning model. We said, fine, so we may not able to solve the problem. Let's, wherever the problem is solved using deep learning, let's build a platform so that we can enable others to solve those problems. Okay. Uh, so we built a platform with all these tools. Like we launched an open source library, we launched an enterprise platform where an enterprise can connect the data and build deep learning models on our platform. We can take care of things like compute optimization, inferencing, for example, model scaling. All those things is offered as a machine learning as a service kind of platform, MLOps, classic MLOps platform, right? We were one of the first around deep learning, but otherwise there were products like Data Robot, Histo.ai, which is already doing around classic machine learning kind of approaches. So this is the early commercial success in deep learning, right? 2012 to 2015.
How do you
Uh,
monetize MLOps? Is it like per API call or what?
No, at that time it was purely around subscription fee, and there is compute cost. So subscription fee is you pay to access the platform, and compute cost is whatever you consumed, you pay for it. I don't control the models, thereby I don't control the API quantum. You would build an image classification model, you will build a text classification model. It could be anything, right? You can play with any of those. Uh, so this was the early commercialization era for deep learning, right? So we were doing tooling, people were doing solutions, people were migrating from classic ML to deep learning kind of part. So 2015 is when there is a lot of like here and there strategies. There is enormous amount of new strategies came in because of the early success of NLP. There was AI bots demand rose up from 2015 onwards, like if and then kind of stuff, right? So what we have done during our STEM research point of view, people thought that is a scalable, which is like exactly the same thing that happened in 1980s, right? The expert-based systems. They said I can scale the NLP problem by building a if and then kind of rule. This is where things like dialog flow from Azure came into play. Meta, which is previously Facebook, has launched bots into Messenger. uh, Alexa got launched at that point of time from Amazon, right? Uh, so this is very important. This is the early stage of a conversational system as a service. People thought these rule-based NLP systems can scale, and hence people started investing around a bunch of bots. 2015, 16, 17 is when people invested a lot on the bots. A lot of research is now focused around creating a conversational capable AI systems. Whatever is commercialized became fall down. They were never able to scale up. Few people have scaled up in very conditional problems. In India, there was Haptic. Earlier, they were called as Hello Chat. It was a customer care service. They migrated to a bot-driven platform. There was Nikki.ai in India that was solving that problem. So Nikki now shut it off. Elo.ai, for example, Elo Networks, they were previously these repositories kind of stuff, like Elo Pages kind of stuff. They migrated to now chatbots. So there were few products that got migrated into this enterprise if then kind of dialogue systems. They were successful for a specific problem statement, like IVR in call. People were okay to do IVR on chatbots, primarily for customer support, right? Like if you have this problem, they were able to localize and then do the next set of conversation. So, but the importance or the attention for conversation systems has gone up at that point of time. NLP has gone up really massively. But you may ask what happened with CV, right? Computer vision. Like we had the early success of CV, but it was not scaled. Uh, the actual commercial value of CVs and things like medicine, for example, like radiologist, or in video or video surveillance, or there is a video heavy problems, for example. Uh, so people were trying to figure out how to use CV in all those commercial use cases. They have applied CV for e-commerce based use cases where a bunch of product SKU mapping and all that stuff were scaled. There are a bunch of startups who came in for that use case. They have done solutioning as well. They did very well. And for NLP, whoever have done this point focus specific enterprise problem, they were able to scale and sustain in the past few years. Tools were able to successful who were doing classic ML. Tools we were doing as deep learning, which is very niche at that point of time. And the success is only largely B2C areas, right? B2B is not that successful. Deep learning is not that successful because of data sets and all that stuff. Of course, if you have a solution, you would have been successful there. But otherwise, this is what the case was. So we had to pivot because we were way early in the market from in terms of deep learning tool set. The community is very small. So we started saying that, why don't we build the end-to-end platform for one industry? Let's create a moat basis on that. Because you have tools, you have models, you have solutions, you have guardrails, risk layers on top of it. You have a lot of things when you start verticalizing. The verticalization is quite deep. If we build it, then that's the mode, right? Because nobody else can build it. It's quite hard. If you apply for multiple use cases, it's quite hard. So we have taken the verticalization approach. saying that let's verticalize the platform instead of building a horizontal platform. There were solutions and da. So 2017 is when we started seeing a new slow transformation around language because of the paper attention is all you need paper and BERT models, right? So again, 2015 to almost 2018, 19 as well, even 2020 also. The research was very much incremental. So it was AlphaGo on the reinforcement learning side, and then you had a little bit of successes, but NLG was a problem, image generation was a problem. So that became main focus of point to solve from 2017, 18 onwards, both for vision and both for language as well. In vision, the thing that happened is the creation of GANs. Uh, GANs were introduced in 2014 odd by Eon Godfellow. So GANs is general adversarial neural networks. So the idea is how I'm able to understand an image. Can I generate an image as well, right? So for example, today you're seeing all this image generation diffusion based models. The early version was GANs. Images has had a little bit of success because of GANs very early on, whereas for text it is still kind of building up, right? Uh, so when 2017 paper came in, the attention is all you need paper. That scaled the idea that when you actually store or make the model learn not only the sequence but also the position of the sequence. Meaning, let's say I am the who is the president of United States, for example. So you have to look at all these tokens and how these tokens are positioned in a sentence. If you remember this sentence location as well, the location of these tokens, then this can and increase the scale of the model and increase the scale of the training data and increase the scale of the compute. You can build a large enough model which can understand the language very well and also start generating languages in a very rudimentary terms very well, right? So this was done by Google at that point of time. Attention is all you need paper, and they launched a bunch of large language model classes called BERT. So BERT is like the OG of LLMs since the beginning. Whoever is doing an NLP or old age AI guy, they would look back and say that BERT is the main thing that they would have always been used. Even today, many people use BERT because it's cost efficient, resource efficient, and reasonably successful when the problem is very much limited, for example. Uh, so this was happened from 2017 onwards, where NLG and image generation started flowing in, but it was never scaled to saying that there's going to be a disruption. It was until 2020s also we were thinking that deep learning is gone because so that use cases is very limited only on classification. Generation is not picking up. Reinforcement learning is not picking up. Computer vision is still in a very rudimentary stages. From a generation standpoint, the commercial success of deep learning was largely on the B2C case. B2B, it's not that much. And even on B2C, it's largely with the guys who had a lot of data. They had an advantage of cost, an advantage of this thing. But people were continue to invest, saying that there is some light at the end of the road where they would have some success, right? That's what everybody is saying.
Uh,
Uh,
I
yeah.
want to ask you a couple of questions here. How is reinforcement learning different from deep learning?
Okay. Reinforcement learning is sometimes class, sometimes not a class. So reinforcement learning has a different kind of learning architecture where you could use deep learning architecture as well, deep learning model as well. So in reinforcement learning, you have a state space and action space and a reward. So state space is where you would probably think of what to do next, and action space is where you would do the action. For example, let's say driving a car, right? When I'm driving a car, I should turn, right? That input should come in the state space. And the reaction or the reward is whether I have done the right step or not is the reward. Which means, let's say I'm playing a chess game. It's quite easy to do on a game a problem. So at each step, I know whether I'm winning or I'm losing, right? Or the probability of winning and the probability of winning, I can calculate. Uh, as long as I take a step where my probability of winning is growing, That's my reward. That's the Q learning part in reinforcement learning. I can use this using traditional Q learning or use a deep learning model to do Q learning. But otherwise, reinforcement learning is also kind of part of deep learning as well, or can be looked at separate tasks also.
Which is why it worked for AlphaGo, because
Gaming, correct.
there is a clear cue that whether the move was right or wrong. Okay,
Yes,
okay,
and the
and
protein folding problem as well. That's the major invention happened in reinforcement learning, right? So there are so many protein combinations that there are infinite protein combinations. So how do you create a right protein combination for a right problem statement? So that's also a reinforcement learning kind of problem.
what what does protein folding give you? I mean, why do you want to fold a protein?
Yeah. So when you design a medicine or when you want to test a medicine, for example, so you will play with proteins, right? So which protein is reacting to which kind of medicine, for example. This again, I may not know exact specific of what's the uses of protein, but finding the right protein for medicine is important. Okay. One
Okay,
for creating the medicine, next to test the medicine as well.
okay,
So the more
okay,
number of good proteins that I can create for a specific use case, the more I can test and the more I can innovate on curing. That's why as that problem is now solved to a very large extent, people are predicting that in the next 5 years we can cure cancer, because now I don't have challenge of protein creation, which was a huge compute problem and a huge creation problem. I can
okay.
have AI create proteins for these specific problems, and
Hmm.
I simply start testing and doing clinical trials accordingly. So I can scale the curing problem quite exhaustively after that.
Okay. And you spoke of diffusion based models. What does that word diffusion mean?
Yeah, so GANs is one approach, general adversarial neural networks. So GANs is you have network input, you have an image going in. That image, you have number of layers reducing, and then in the first set, in the first component of neural network, you will start decomposing the image. In the second set of neural network, you will start composing the image. And if you see whether your input image and output image is almost the same or not, this is the GAN model. In a diffusion model, you have a diffusion kind of neural networks where you add a little bit of noise into the neural network, and you try to rectify that noise. So as long as you're able to create an image by able to addressing this noise as well, you can create an image properly. So diffusion models are scaled very well in image generation today. You take any example of text to video or text to text or text generation itself or text correction, for example. All of them are based on diffusion based models. Okay. Uh, yeah. So net what happened is 2017 is when we have seen a bunch of new ideas coming in, right? But as I said, I think until 2021, 22 also, we never thought what the scale was or what the next inflection was, because always year on year the increment was very much organic, like we have seen next iteration of an algorithm, next optimization, next better compute optimization, for example, like that. But what's happening in the background was there were very few companies who are investing on the idea that the larger network, larger data, larger compute is the answer to the problem. Think back 1960s, right? So 1960s, the network size is quite small. Then we figured out that in 1980s, that if the network size is a little bigger, it can learn properly, but we don't have the compute. In 2000s, we were able to scale the network, but we didn't have the data and the compute. But now in 2020s, we had good enough compute, we had good enough data, we had the algorithm and the learning logic, right? So it's an evolution of almost 70 years before we got to a stage of 2020. And this has not happened with large organizations. That's a surprising thing, right? So because nobody believed in this idea, so nobody thought this is an idea, for example. But OpenAI thought this is a good idea. OpenAI or Stable Diffusion, for example, like OpenAI when they started in 2016, 17, 16, in fact, their idea was to invent or invest around disruptive ideas. So they went in a similar route of DeepMind in the beginning. They were building robots, state-space models, action-based models, for example. But when the attention is all you need paper was there, BERT was there, they started investing around building larger set of models. There was Microsoft who was also building large models. There was Google building large models, and there was OpenAI building large models. So their GPT-3 model in 2020-21 was one of that early model. But the success was still very rudimentary, right? That was the same year where AlphaFold 2 was there. The protein structure prediction model was successful. GPT-3 got launched in the same year. But if you ask any NLP researcher or any AI researcher at that time looking at GPT-3 output, they would have said, this is just gibberish. Because we were doing that even 3-4 years back as well. So what's different? There is not much of difference in what GPT-3 is doing versus with other players. But OpenAI was reluctantly investing in larger model, right? And then there is RLHF as a technique that they introduced around the model to fine tune and make the model specific to a certain task. This is the when OpenAI launched GPT 3.5, it was extremely you could call it as a simple update in their research, right? So they had to show some update to investors because they were non-profit and they raised a bunch of monies, close to $1 billion. They were investing serious $1 billion on compute. Then they launched 3.5. People suddenly started realizing that it can able to generate text really well, really, really, really well, right? As good as a human and sometimes better than humans, at least in certain kind of problem statements. So this is the inflection of a new AI era, right? But the conclusion was you need large data, large model, and large compute. As long as you can scale all these three, you can solve a problem. This is demonstrated in text. This is demonstrated in protein structure. This is demonstrated in images. That's when it became like whoever wins the jackpot will become the winner of it. For example, so then people started investing heavily on building such large models, large data sets. Compute was invested like anything else. This is the search for NVIDIA demand going up, skyrocketing heavily in terms of building these kind of models, for example. So this is the new era for now the new era of large models. You can call it last decade was primarily perfecting the deep learning scale. Now we are applying that scale. So we are primarily applying that scale for from this year onwards, right? So there is a certain guarantee of predictions like an AGI, all of this because now we know that this is a function of scale. But it's not without criticism for sure, right? Like Jan LeCun, for example, he's a very, very strict criticism around LLMs because these are next token prediction, right? Auto-regressive models, which are predicting the next token. As I said, learning the token and predicting the next token, for example. But in reality, there is a limitation of how far you can achieve from these kind of models, right? Let's start with reasoning. You mentioned about prompting, for example. So typically, what happens is you give an initiation to the LLM to generate the text. This is what your prompt or question, whatever it is. You are creating the first initial set of sequence, and the model tries to complete the sequence, right? Now there is a bunch of questions right now, right? Is there a reasoning while generating the sequence? Or is there a conscious while generating the sequence? These are the two big questions right now. And then the third question is around how is the model functioning to generate the sequence, the explainability part, right? Uh, now, the way to generate the sequence properly is giving the prompt properly. One is, of course, I can increase the size of the model, but if my prompting is not good, then the model can always fail in giving that output. Now I have a trillion tokens kind of model, billions and billions of tokens the model is trained on. It becomes quite hard to be able to create the right prompt for your problem, right? This is where the reasoning came into play. Reasoning is how well I can draft the chain of thought. Chain of thought, as in the sequence of prompts in a manner that I can make the model give the best in a very less resource intensive manner. This is one thought of school. Second thought of school is I will make the model think more and more and more before giving me the answer, such that I can utilize the humongous amount of learning that it has. But instead of restricting the output time to, let's say, 1 minute, I'll increase the output time. So this is the test train compute, right? Test train compute is instead of taking the inferencing at instance, I'll increase the output time. I'll make the model think more and more before giving me the answer, such that it can able to, or it should be able to solve more complex answers, right? So you have seen early prompt era in 2012, 2021, 2023. And then you have seen chain of thoughts in 2023. You're seeing reasoning in 2024, late 2024. Now you're seeing test and compute being scaled. Like if you used the capabilities like deep research, which now every LLM tool has, deep research is nothing but making a model think more and more and more during the inferencing time, such that I can able to solve that problem, right? So people have done experiments to prove that if I give, let's say, one full day, to think, what would model give me as an answer? Versus if I give you 1 minute, what would model give me as an answer? So for problem statement, something like, let's say, theorem proving, right? I want to prove a theorem, for example. If I can increase the compute, I can make the model prove the theorem. Uh, this is why reasoning models are getting increasingly better in solving the Olympiad level mathematical questions, because now it has more ability to reason, not think, reason and also time to think from that point of view to give you that answer. So there are two things happening. One is I'm increasing the scale of the model and I'm increasing the techniques around reasoning such that I can get the answer. But the question always comes is this the path to AGI, for example? So that's always the question that comes back to it. But yeah, so this is the current era of AI where we are using such large LLMs to do multiple things. But you will go back to the same cycle of AI in every generation, right? So you have a big innovation. Now it needs enterprise acceptance and actual commercial scale to come out of it. Then only we can see next immediate cycle. Um, in the last whatever years that we have seen so far, there was no continuous validation of experiments, because that's the mistake that we continuously made, which is over expectations, right? So we always hyped the AI cycle in each every point of view. uh, is this hype cycle also the same or not is something that we have to look at in the next 2 years in terms of what we can deliver from a commercial capability of the AI, and then validate it. Of course, the hype is beyond the reasonable value that we can generate today. But the hype will get corrected, or it's already getting corrected. So we will probably match the hype in the next maybe 3-5 years. And that's the other beauty of AI as well, right? So the test and optimization cycles are reducing further and further. Like in 1930s, it's almost 40 years, sorry, 20, 30 years for testing, and another 10 years for correction. 1980s, it's 10, 15 years for testing, another 5 years for correction. And 2010s, we have seen testing being 4 5 years, correction another 4 5 years. Now we are testing like hell, right? Like everybody is an AI company now, so everybody transformed into a bunch of experimentation around AI. We are testing multiple things, but we already have very great success areas. Success areas like a code interpreter, for example, is massively success area from a productivity standpoint. You have a content generation is massive success area. Customer care, customer chatbots is a massive success area. So these are the areas which were not non-existent 2 years back or very mildly existent. Now the value add of them is massive. but there are multiple things which it is not good at. Like for example, fully autonomous decisioning, for example, right? Even though it can make a decision, the next complexity is around explainability. If the model is so complex, how do we understand it such that we can make the model, we can get the satisfaction of the explainability to all the stakeholders, for example. So this is where we are currently standing. We have large set of models where we have certain successes, and then we have obvious challenges, which is around explainability, auditability, alignment, being one of the most complex problems to solve for us to get to that next stage of commercial scale for AI.
Okay, fascinating. Um, what is RLHF?
Reinforcement learning human feedback. So when a machine is generating an answer, right? So you will give whether it's good, bad. Like as I said, the RL environment is you will take their feedback. Feedback in this case is good, bad, for example, or you will give an examples of good answer. In both cases, the model optimizes how it's generating the text. Okay. So there is something called pre-training. Pre-training is you ran the model across this massive corpus of data, and then you end up with a model, which is what we call as a pre-trained model. Next is fine-tuned model. Fine-tuned model is you apply RLHF on the pre-trained model, such that you are fine-tuning it for specific tasks. Like for example, conversations, coding is a specific task. So if you see an LLM version, like Llama version, Llama Instruct model, Llama Chat HF model, for example. So these are fine tuned on those pre-trained models.
Okay, okay, understood. Uh, what is the G and P and T in GPT?
T is transformer. I forgot the full form as well, but T is transformer. So it's GPT's transformer.
What is a transform? I think generative pre-trained transformer, right? Like the so what
Correct.
is transformer here? Like pre-trained, I understood.
Yes.
Like it is fed like a large set of data. That feeding data is called pre-trained, from what I
Correct.
understand as a layman. Generative means it can generate that NLG that you were talking about, the problem of not
Yes.
being able to generate. What is transformer?
Yeah, so Transform is the attention all you need paper that I mentioned in 2017, which got published. You have CNN kind of architecture, right? You have convolution neural network, you have recurrent neural network, and you have Transformer is an attention-based neural network. What it does is whenever a few autoregressive tokens passes through, it remembers the attention and corrects the attention from time to time. Okay, so it's an attention-based model. So that's a transformer model. That's a transformer architecture.
Okay, okay, okay. Got it, got it. So recently, I read a lot about distillation learning
Yeah.
uh, because of DeepSeek, which is the Chinese AI LLM. What is that? What is
Oh, yeah.
distillation learning?
So distillation is you take a very small model, but you fine tune it on highly distilled data created by a larger model. So now you have two models, right? You have a teacher model and you have a student model. So student model is a very small 7 billion, 3 billion kind of llama model, for example. Your teacher model is a very big model, like something like OpenAI, for example, right? Your teacher model will give examples, the RLHF, as I said. So convert that into RLAIF, AI feedback instead of a human feedback. Here, a large model is teaching a small model on a specific examples in a very, very constructive manner that the small model can learn very quickly. So I'll give you a few examples, right? In any generative task, be it image, voice, text, the quality of data, fine-tuning data is quite important. It's not just the quantum of the data. For example, let's say I want to replicate a voice, right? I need a good 30-second or a 1 minute voice. Now we are able to replicate even on that 1 minute, 30 second because of this ability. Next, on images as well. So you have things like Flux, for example. Flux is as a diffusion model where I can fine tune image generation even on 10 images. All I need is 10 good images, right? Similarly for text as well. So distillation is I'll create those examples quite good, quite well, such that the smaller model can learn very quickly instead of having to scale my training data so much. I can have so little of fine-tuned data so that this model can become as good as my teacher model, at least in a specific function. So this is a distillation process.
Okay, okay, okay. In a way, instead of feeding it with 1 trillion tokens of data, you have it mimic a model which has been fed 1 trillion tokens of data. So,
Yes.
like, fake it till you make it. Like, that's like a
No, you're making it, but very small example
right,
for a very
right.
small example. That's a distillation
Mm.
kind of model.
Okay.
Uh, Now there are yeah, so this is an opening of a humongous amount of fascination, right? Let's go deep on the rabbit hole for a moment. So one is on the explainability side, for example, as I said. So earlier, if you remember our AlexNet, for example, so we were mapping the activation maps to understand which neuron is important. There, I can do it because it's, I think Alex said is about 60 million neurons. Here, I have 1 trillion token, 1 trillion neurons, 1 trillion plus, half a billion plus, 100 billion plus, billion, B for billion, right? Uh, Now, how do I understand what the model is, how the model is working, right? Why this is important. So, alignment is quite important. Alignment is nothing but I want the model to learn or act in a certain manner. It could be in terms of as simple as a risk. Like I don't want the model to be exploited for certain cases, which is where you do things like guardrails, some kind of taping, for example. Or I want the model to be non-biased, such that it is in my training data there could be a bunch of bias, right? Uh, or it could be on the risk part as in how well the model is giving the answer, the hallucination part, right? Or fourth is exploitation. So how well the model can stay true to the model, not being exploited by someone who is attacking the model, for example. So alignment could be in all these things, and then you also have regulations and societal factors as well. So if you have such a big model in place, how do we align the model, right? Or how do we even understand the model? So this is the next biggest problem, because if I can't do that, then all I'm doing is I'm hoping that by building a larger model and by correcting few things in examples that I've tested, the model is perfect, which is not the case. We have time and time and time in all the previous versions of LLMs. Every version of LLM was hacked, right? Was jailbreak, was made to act in a very different kind of model. This is where it gets really interesting in terms of understanding how the model work. This will be our next step to say design an AGI, for example, a good AGI. Or else we will probably create an AGI which we will not understand and probably could be exploiting a lot of things. For example, let's take the reasoning part itself, right? There was an experiment done with an LLM where with a reasoning model, if I'm not a reasoning model, correct, to play a game with a user. So what the and the success is winning a game, right? Uh, Instead of playing strategies like what we used to do in AlphaGo or chess game in the past, this model figured out that there is a back route for the gaming algorithm. It exploited it and won the game. Meaning, it didn't play the game. It exploited the algorithm and tuned it in a manner that it could win the game, right? If I want, this is what could happen. For example, let's say I want a best formula where my country is growing at a 10x, for example. It could always come up that it may tell you to kill somebody or to attack somebody, to do some things, or do that in the backend as well. This is the biggest problem with the reasoning and the agents that we are talking about. How do we control the planning, and how do we ensure this planning is happening within the specifications of alignment requirements that we have? And the third part is how to do planning efficiently. If we solve these three problems, that's our route for AGI to some extent. But of course, this current architectures of transformers may not scale. This is where Jan LeCun's criticism is. Meaning, in a realistic environment, if you take a dog or a cat, it does thousand things well in a given second by doing a lot of things. It's not simply looking at language. Um Currently, all LLMs or LRMs, large reasoning models, are language heavy. You have to migrate from language to images, videos, multi-model, and the entire state space, action space. Then you could know that if a given environment, how to act, how to behave, or how to work, for example. So this is why Jan LeCun is working on a new architecture called Zeppa. Uh, Japa. I think I'm saying it right. Japa. So Japa is something that he has been front ending for quite some time, almost 2 years now. But he believes that's the architecture where you could build systems like this. But necessarily, the belief is we will probably stagnate on the current approach sometime in the next 1 or 2 years. We will see new areas of next set of commercialization, which is where agents is next set of commercialization. People are doing less on the LLM part. People are now doing more on next LLM. What next can I do after having an LLM, for example? The agents, planning, and all that stuff. That will probably gain a lot of attention in the next 2 3 years. But from a fundamental LLM point of view, we are largely getting stagnated. Uh, we are seeing one architecture migrating to another architecture, trying to match a similar kind of accuracy or a delta kind of accuracy. This is very evident in GPT 4.5 release as well, right? It's not the best model, but it's just good model from all these perspectives because we are largely now stagnated on this. So we will see a lot of innovation after this on the agent space, reasoning space, planning space, and explainability and guardrail space. But whereas on the fundamental new architectures to create AGI, probably we will. There could be some architecture which, like attention is all you need paper kind of stuff. Somewhere the idea would have been already published. That's for sure because all ideas will largely recreate and regroup. Or there could be something else which we have not thought through in the last 70 years, which will suddenly come and become the soup or the recipe for AGI.
Fascinating. Let's end with a little bit update on Arya. So, what have you? So, you said Arya was at the tooling layer in 2017. What's
Yeah.
been the journey since then?
Oh yeah. So we pivoted to being a tool and platform and started verticalizing for financial services, right? So that's the biggest moat. In fact, that's what we keep on telling to people. Your moat could always be on verticalization, irrespective of the algorithm, right? That always stays true. Your moat can be on the algorithm, but you have to be very quick, which is what OpenAI is. Your moat can be on the tools, but you have to invest in a very long term, right? Like Data Robot, for example, it's in the journey for the last 20 years. To build another new platform, it's going to take time. So, which means you have to have a lot of patience to be becoming a platform play, which is one of the toughest plays, but very sticky game if you become successful. We are into that verticalization game. So we said these layers largely remain keep on changing, but the end use case will always get improved over time to time whenever there is a new addition, right? This we created as a PaaS, platform as a service for financial services, which is banks, FS, and insurance. We created from ground up because we started off as a platform and then we created a bunch of pre-trained models and fine-tunable solutions. And we have been deploying this as a service for the past 4 or 5 years is when we started scaling very well. This is growing very, very good. But now the important problem that we definitely need to solve for the sake of ourselves, for the sake of the industry, is the explainability and the alignment part. In fact, our experience was actually pretty much firsthand. So we built a deep learning model and tried to deploy it in an financial institution. We got rejected by a regulator and the risk manager because it's not explainable. No matter how accurate the model is, but the model is not explainable because you couldn't understand what's happening inside the model.
So,
There are
just to
techniques. Yeah,
like give an example, like say, if I apply for a credit card with ICICI and my application is rejected, ICICI should be able to say why it was rejected. Now, if ICICI is using a machine learning model, it will not be able to say why it was rejected because it can't peek inside how that decision was made. The decision is probably a good decision. It was the right thing to reject, but why is something which the model cannot answer. And that is where explainability and reasoning, the importance of that comes in for financial services
correct.
specifically.
Absolutely. So explainability is the most important thing in financial, highly regulated industries, right? Not just financial services, but highly regulated industries, high sensitive industries. So, for example, if I'm a doctor, if I tell you you should do cardiac surgery, but I can't tell you why, then it's a problem,
Yeah.
right? Uh, uh,
Right.
uh, and I'm let's say I'm running a fully autonomous spacecraft, and it got failed. So I can't tell why the spacecraft is failed. Again, a problem. I'm running a full run oil rig, fully predictive maintenance, all of it, and suddenly there is a bunch of error. So net, wherever there is regulations, there is risk of value, risk of life, risk of society, like governance, for example. If I'm only giving credit to certain class of users, not to certain class of users, and I can't tell you why, then again a problem, right? So explainability is fundamental requirement in all of this. Second requirement is a risk, right? Meaning, in all these use cases, it's not just that how accurate you are in those, let's say, 80 cases, but it also how inaccurate you are on the remaining 20 cases. The false positive value is quite high. You can't be wrong inconsistently. You can be wrong inconsistently. Then that's where the risk management comes into play, right? If you say that I can perform 80% all the time for this class of data, then the next job is for risk managers to figure out how to bridge that 20% gap where the model fails. But the problem with models is they act very erratic, right? Because sometimes they may be doing very good job, sometimes they may be doing very bad job. So how do you deliver that consistency? This is where the alignment also comes into play, right? And we are only talking about the beginning of the problem because we are talking about a very small size models. If the model size is going to grow as much as an LLM, for example, there is no way you can use them in scenarios like this without solving these problems. So this we faced on first hand, and we realized that this is going to be the reality, right? Because in the last few years, we already have seen that modeling is now not easy. Sorry, not tough. I can go from a data to a model very, very easily right now. There are a bunch of tools, there are a bunch of AML. Now there is going to be a bunch of AI data science agents where you simply give data, the agent will give you the model, or a human will give you the model. But if you can't explain and solve these problems of risk and alignment, you can't use them in very serious scenarios. So this is where we will now see a new evolution of ecosystem, right? Like how you have seen evolution of ecosystem probably in 2000s. There is one class of people who is publishing software. There is one class of people who is auditing, managing the risk, doing cyber risk, for example. So this class of auditing slash risk management ecosystem is now started emerging. That's what we are solving for the past 2 years. Because of being an early player, we had the advantage of playing with large models, users, and all that stuff. So recently, what we did was we released a new technique called backtrace. So what it does is, so a neural network, you will pass the data, and each perceptron or neuron, it gets activated, right? As I said, what backtrace does is it will picks up your output and tries to calculate relevance of each neuron by analyzing this activations across each node. Uh, I can scale this concept even to an LLM today. So we applied that explainability to an LLM, to mixture of experts kind of models, a large set of models. We have created this as a new R&D slash product group called AryaXAI. So we have this traditional Arya.ai, which is the PaaS as a service, commercialization around solutioning of AI. And then
So
this
uh, the traditional
yeah,
Arya.ai would be, for example, customer service for banks, or
underwriting
processing credit card
models, fraud
applications,
models. Correct. Yes.
insurance claims, those kind of things. Like banks would be automating their routine workflows with the traditional Arya.ai. So it's like a co-pilot for the, like, say, the credit manager has a co-pilot which helps him to take better credit decisions.
Yeah, so not co-pilot, but actually an underwriter, actually an expert, for example. So the job is to replace an underwriter, right? The job is to replace or fraud detection systems like that. In some cases, we are co-pilots. Like in fraud detection, we amplify the ability to identify fraud. But Arya.ai is primarily around solutioning and commercializing AI. AryaXAI is primarily around the explainability and alignment, interpretability and alignment of AI, which is a larger problem, more universal kind of problem. Uh,
So that is no
we
longer
have
vertical. Like AryaXAI is more
that's not okay. Yes,
horizontal, and that is not like a bank wouldn't be buying AryaXAI, but maybe somebody who's serving a bank, like a AI
yeah,
vendor to a bank, like say an Infosys might want to buy AryaXAI because
RxAI, correct.
okay, okay,
Correct.
okay.
Anybody who's building a solution for mission critical, they would want to use AryaXAI as the
Mm-hmm.
inferencing stack, right?
Got it, got it.
So now the next big bet is by doing interpretability, by understanding what's happening at each neuron. Can I modify the behavior, or can I do a bunch of things? So our early research, which we are going to publish, or other people also have published, is I talked about localization in human brain, right? So our brain intrinsically localizes certain areas for certain things. So in LLMs or in very large deep learning models, this is exactly the case. Certain neurons are extremely important for certain things. For example, there was a paper published which observed that certain neurons are extremely important from security standpoint. If I tweak those neurons anything, then it becomes easily hackable or easily attackable, for example. And certain neurons are extremely responsible for biases. The gender bias, ethical bias, for example, when the model learns, it is observed that certain neurons are responsible for this. So this is what our next big research area is. By doing interpretability and this, can we do alignment intrinsically inside the model and introduce new techniques around alignment such that let OpenAI or people like OpenAI publish models. We ensure these are interpretable. We ensure these are aligned such that for the end user, they get the advantage of solutioning, right? If you look at the regulations, the risk, or the value, everything is at the point of source, which is the guy who's building the application. The regulations applies on them, the risk is on them, the value is also on them, not the guy who's providing the models, right? Not the guy, not the OpenAI. It's eventually the guy who uses OpenAI and build a solution and creates this is where the actual value is, or the actual risk is, or the actual regulations is. So that's where we are going to play as part of AryaXAI. This is a very interesting problem. Very few people across the world focuses on this problem because it's a very hard problem. Like Anthropic has a mechanistic interpretability team, which is doing similar kind of work. Their approach is a little different than ours. There's within OpenAI, there is no department like that anymore. Google has a certain team right now. There are few labs in Europe who is doing this kind of work. Now we believe this is a big area, right? As I said, so modeling is one thing. Model acceptance is a whole new game, which is where RAXAI is going to play. So we are even, yeah. So we even launched a new research lab in Paris, exactly for that reasons, because Europe has very good R&D talent around these kind of problems. Our idea is we would want to become one of the most important labs around these two topics in the next 1 year. So that's the goal that we have.
Uh, are you like a profitable business, the Arya business, or are you a lab? Because when you say a lab, it is essentially like something which needs investment, not yet profitable. So,
Yeah. So
what
you
is
can think
your
of Arya.ai and AryaXAI as like something like DeepSeek, right? So DeepSeek is a lab for them, whereas the commercial is their hedging slash the algo trading business, right? So Arya.ai is a profitable business. So there we commercialize and productize AI for a bunch of players in financial services space, and
what
we
revenue
recently
do you
got
do?
a sorry.
What is your ARR,
Uh,
annualized revenue?
it's not a public number, but I can tell you that we are EBITDA positive for the past 3 years. We are growing 3x in the past 3 years. We recently got acquired as well, which gives us more firepower to play with. Right. So Arya.ai is our bread making business. It generates revenue, it generates
Is it like
customers. Yeah.
broad 50 crore to 100 crore revenue range?
Yeah, around that numbers. And we will be more than that in the next 1 year for sure. Because there is enough demand there for sure, right? AryaXAI is an early stage startup from that point of view. So we are very early in that point of view. We recently got product. We recently started productizing, even though we have implemented it as part of Arya.ai. So this is the other advantage that we have, right? So we have direct access to customers. We are using deep learning and coupled with AryaXAI to deliver the promise of the statements that we are making in AryaXAI. Uh, in that way, we are we have a very good edge. Like we are not purely experimental, we are experimenting and also optimizing the product. But the largest value that we are going to see is when we solve this problem of alignment, which will probably in the next 6 to 12 months. When we launch product around that is when you could imagine us launching something like, a Hugging Face for high mission critical kind of platforms, an AI inferencing platform where you can bring in the model, but we will handle everything that is required for a mission critical area, for example. So that could be a new thing, but that's at least 9 months, 12 months away for us. Right now, the focus for us is on the R&D part. Uh, as I said, this is a very important problem and a very complex problem as well.
When you're EBITDA positive, why did you choose to get acquired? Why not
Oh,
continue to build independently?
yeah. So there are two things when you grow business, right? So one is growing business, growing product. We were able to grow business because we are small. But that doesn't mean that that gives a guarantee of growing in the same cycle for the next, let's say, 4 5 years. Like growing to, let's say, $10 million business is extremely different comparing to 10 million to $1 billion business. 10 million to $1 billion businesses where you need larger processes. Your focus moves from product to scale, right? Scale is where you look at. Product actually takes very less of a backseat many times. Pretty much 100% of the times, product is a backseat. R&D is a backseat. Acquisition is a good route from that point of view, right? So Aurionpro, our acquisition partner, already has massive distribution access in the financial services space, which means we don't need to do the selling. So the selling is already done. We simply upscale the product.
Aurionpro
Uh,
is a like a IT services company for financial for
it's
BFSI.
an enterprise product company out of India,
Okay.
and they are public company as well. So
Hmm.
they have ARR more than $100 million year on year, and they are
Wow.
growing quite well, very profitable.
Hmm.
But they are a product company, unlike many other services company that are there from India.
Oh, okay.
So
Okay.
this is a
Fascinating.
nice combination, right? So
Hmm.
and
Hmm.
that's
Hmm.
why we are
Hmm.
now focusing on AryaXAI, or else
Hmm.
we would simply have to focus on scaling Arya.ai to multiple markets,
Right.
deploying it and all that stuff. We will do
You
it,
can.
but yeah,
Yeah, I mean, you can piggyback on the Orion Pro sales infrastructure because they would already have
exactly.
the infrastructure to sell to BFSI. Okay, got it.
Yes,
Interesting.
correct.
Okay, interesting. Fascinating.
Yeah, so this is the next phase for AI for sure, as I said. So one is we will see migration of problem statements. We will also see the maturity in enterprise architecture. uh, you will see pretty much what's happened in software in the last 20 years, right? Like from 2000s, for example, you only had application, then you had application monitoring components, you had application security components, and then you have cloud component. How you have seen software maturing and a dollar investment spreading out. That's how we will see for AI as well. That is also what happening, right? The investment around the models is kind of coming down. The investment around the models is going up, which is the solutioning, security, and all those kind of things.
Mm.
Yeah, so this will be a great opportunity, and we are highly positive than in the previous cycles, because as I said, there is more data, more compute, more number of use cases than ever. So which means there is larger opportunity to commercialize as well.
Mhm. Let me end with this one question. There is this whole class of startups which are putting a wrapper around AI.
Yeah,
Uh, and I mean, some people are critically calling it wrapper around AI. Maybe it's not necessarily that, but say for example, I as a podcaster use a tool which takes a podcast recording and creates an article out of it. So, like we had a conversation, I'll put this conversation into a tool and it'll give me a nice 1500 word
yeah.
blog. Do these kind of tools have a right to exist? Would the fundamental models eventually be good enough to that you just need a subscription to a Gemini, for example, and it does everything for you?
Yeah. No, I mean, let's go back to 2010s again, right? So there were a bunch of models, which is AlexNet, Clarify. These are the models that came into the market. But the commercial value was always on the end applications, like using it for image labeling, SKU automation, image description kind of problems. and in enterprise problems like ticket rerouting and all that stuff, and customer care bots, for example, right? So the end applications is going to increase their value proposition. What's happening on the ground models, for example, like whatever has happened at the LLM, eventually things like your intercom, for example, is a good example. Intercom is being classically the customer care software. Now it's automating the customer care. Next, it will fully autonomously run the customer care, right? That end application value has exponentially gone up, is going up from time to time, right? There is a clear value. So if you are already in that business, your ability to multifold that is now the best opportunity that you could have. It all depends upon how quickly you can add those features and components so that you can become a big player. So this is why the enterprise AI is the biggest opportunity right now, for two reasons. One, for disruption, for of course. Second, for the current stickiness of the enterprise applications that you have. Most of the current enterprise applications are legacy. Almost 80% is legacy. 20% is fresh, which has happened in the last 10, 15 years. Even they are now legacy because not all of them are API heavy and all that stuff, right? So whoever is going to deliver that value in that end application is going to win that game. That's what. Like even the podcasting, for example. So podcast creation and organization is a service. Summarization and everything is additional value add the service can deliver, right? This will stay true. The TAM is gone up for these end applications. Hence, you are betting on acquiring more of that increased TAM if you're already in this player. Or if you're a new player, your proposition is I'm going to disrupt because I'll do things faster than anyone else. This is what happening in sales side of things right now, right? Because of the agent space, the classic CRM tools which has been there, like Salesforce, HubSpot, for example, are now migrating towards to agent-based sales CRMs. There are people like 11x, not 11x, and then there are two, three other players in US who are agent-heavy CRM systems. They said, I don't want this 100 screens to do the job. I'll do this through agent.
Yeah,
Now I use
AI is the
yeah.
new UI basically.
AI
Like,
is a new UI. Correct. Exactly. So that is happening there. Correct. Um, but and now you see a lot of intermediary players now. So there is a clear value there. There is a win there for sure. And then there is a tooling game. Like I'm taking both extremes. Tooling game is extremely hard, extremely tough. The mode is decreasing day by day. Tooling slash platforms, like for example, cloud platforms, right? So people are okay to use things like Together.ai, Nebius, or RunPod, for example, to run their GPU experimentations, not just using AWS. In some cases, enterprises are also okay as long as there is a data guarantee and there is closeness and all that stuff, right? So the data center and cloud component is getting disrupted very, very quickly also on the platform level. Platforms like DataRobot, Databricks, which has been classic MLOps, they migrate towards being a CRM systems, uh, which is, our prediction is most of the software will become point of records. They capture the point of records and action happens peripherals. This is what Salesforce have become, right? Even though it started a CRM 20 years back, 25 years back. But currently, if you look at CRM, you will do very less things on CRM. You will do things more around the peripherals. You have calling system, which is integrated to CRM, which does the calling at the end function. You are simply sending the record there. So in tooling, that opportunity is now emerging, which is where AryaXAI is also into, right? We are not replacing your current base MLOps platform. We are adding into it. This is now becoming interesting because things like compute optimization, security, data distribution, compute distribution, for example, all these things are very interesting because 1% saving in value is close to $10 million for a big business, right? There, it's a very technical driven game, very high technical moat. There, if you are from that background, if you have done that, did that, and you are migrating into the business, you have a better value of success because you know what delta you want to add in the tool part of it. It's tough to win, but if you win, you will become a long term player. And then you have foundation models, right? Which is OpenAI, which on the tools part, for example, OpenAI and all those guys, foundation models. And then you have foundational training data. Let's call them as training data providers, for example, foundational training data providers. They had a large amount of success in the past 3 years, like Scale.ai, for example. There was a couple of other companies in US who suddenly are doing $200 million ARR from a $5 million ARR in the 4 or 5 years back, because all these large companies need a lot of training data, right? Training data, labeling, corrections, all that stuff from images, videos. They will continue to grow. They will continue to grow for the next 5 years for sure, because you have new type of data. Reasoning is a new problem. They will always say, I will now provide PhDs on a payroll, not just plus two guys on a payroll right now. They will provide expertise because to evaluate reasoning accuracies and all that stuff, right? The training data providers who already have been working with them, they are growing very, very massively. Now the foundation model story is kind of shrinking, right? Shrinking and expanding, shrinking and expanding. It became like a sponge. It shrunk to only one or two players about 3 or 4 months back, and now suddenly opened up because of DeepSeek, right? Suddenly opened up saying that no, 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 you can even small players can become that foundation model providers. Um, so you everybody can always build foundation models or SLMs as well. People are even pre-training the models internally inside an organization as well. I've seen the cases to that extent also. But there is always a value of OpenAI. Nobody can replace that. So you will have OpenAI, Gemini, Anthropic, maybe three or four or three. It'll consolidate to that. And then you have a bunch of small SLMs playing in, either saying build your own SLM or build on top of my SLM to some extent, for example, or a reasoning model or an agent calling model. You see a bunch of new opportunities in playing in this area as well. Here you can have a game of more than one player win kind of strategy. Here you could see a bunch of startups who are already raised, let's say $20 million, $50 million, uh, trying to win this game. They can't win this game because nobody is now funding them that anymore. Even Mistral probably don't do that. He'll probably do this part of it, right? So investment is kind of diversified, saying that okay, you are building an let's say LLM for robots. Okay, I'll give you $50 million. You are building an large model for agent calling. Okay, I'll give you $10 million, because there is a value in those functions. The idea is, let's say a billion call happens, you will get a share of that billion calls, and then you will get profitable there. Next is the mid-layer solutioning, right? Like things like RAG as a service, for example, Q&A on documents, for example. These are the biggest risk, because for all the large models or small models, they'll always go into solutioning to try to extrapolate their value. This is why OpenAI is the biggest competitor to every other player in this segment and has been disrupting it from time and time and time. 2 years back, RAG as a service was a big proposition. Like people were saying that I'll use OpenAI and build Q&A on top of it, and that it's entirely vanished. In 6 9 months, entirely vanished. People have done RAG, entirely vanished, or they've scaled only in the enterprise segments, for example. There, it's a very tough game. It's a very, very tough game. Particularly if the moat is very small. If the moat is only using an application and create that end application to enhance it, people will say the end solution guys or software guys, they simply say, I'll rather buy from OpenAI and build the model or do that service as a service or build it internally, for example. Here is where you would see a bunch of SaaS players trying to play in that game, which is what the biggest threat is. The traditional SaaS always used to be one up as a service, right? If you look at last 5 10 years of SaaS evolution, there is CRM, there is data cleaning, data augmentation, or conversation systems, for example. Each independent one up was a SaaS product, and people were able to create a portfolio of, let's say, 10 SaaS products to serve a function. That's not there anymore. That won't be there anymore in AI for sure. There will be a lot of consolidation, which one try to get into another, one try to get into another, one way or the other. So the moat is quite hard to defend in that case. You may not have 10 SaaS opportunities. You may have 3 4 SaaS opportunities, 3 4 SaaS companies playing in that game, right? This is the biggest pain point in the industry right now. So people don't know where they are playing, what is their moat. Hence, they try to get disrupted or they try to get a huge amount of competition suddenly, and they are not able to scale. Or they just simply consolidate and become a part of another product as well. This is what is going to happen. So all these layers is trying to mature, and this layer of as micro SaaS play, it will not be there anymore. Unlike in a software SaaS, it used to be that. But this SaaS is definitely dead. This is what when people say SaaS is dead, this is what is largely kind of going to die.
Mm. Fascinating. Thank you so much for your time, Vinay.
Sure, awesome. Thanks, Ashad. See you then.